Hello everyone and welcome back. As you can probably see, this is the first video from me in about 1 or 2 weeks. That's because I haven't had time to actually make the videos. I have had a lot of work to do and things like that. But today I did have a free Friday afternoon, so I thought I would make two videos in quick succession. The first of these videos is what you're watching right now, and it's about the oblique projectile, or basically projectile motion in general. And the second video will be sort of a follow-up, which we'll be looking at the projectile motion on an inclined plane, which can tend to be a bit complicated, but I believe that if you look at it in a particular manner, it's just the same thing, but with some additional equations and things like that. So the reason I actually chose to do projectile motion is because this is the first daunting topic that most 11th graders studying physics actually encounter. I mean, up till here, this has been basic kinematics, V is equal to dx by dt, A is equal to dv by dt, and so on. But this projectile motion that is the first real application of all these things that you've learned into something that's, I believe, really interesting to see. So, well, what is a projectile really? So, a projectile is simply a body that you throw up at a random angle to the horizontal, and you let it fall under the influence of gravity. So, what we have actually done over here is we have plotted the path that the projectile will take by taking into account the motion in the vertical direction, which we have denoted by y, and the motion in the horizontal direction, which we have denoted by x. Now, a distinction that I would want to make here is that this is not your x versus t graph or v versus t graph, which is something that I've seen most people get confused over, because up till now they've mostly encountered x on the vertical axis and t on the horizontal axis. So this is something that most people get confused over, and they try to rationalize it using that. But this is something that you really have to focus on, is that it's actually position on both the vertical axis and the horizontal axis. So it's both positions. So what we'll now look at is we'll try to get some general equations. We'll actually try and get the feel of the topic. So let's begin here. Alright, so the first thing that you have to understand over here is that we're going to decompose the motion of this projectile along the vertical direction and along the horizontal direction. Now the way we do is, so the reason as to why we do this is because we can then reduce it into scalars, and then we can work with them as we please. So what we'll start by doing is write a few constants for the various things in both directions here. So what I'm going to do is, first I'm going to write the velocity in the horizontal direction, and I'm going to let it be ux. Alright, so this is the initial velocity in the horizontal direction, and then I'm going to also write uy, that is the initial velocity in the vertical direction. Now ax is equal, that is the acceleration in the horizontal direction, is equal to 0, because as we said earlier, there's only gravity acting. So there's no other external forces, that we're not considering air resistance over here. So ax is equal to 0, whereas ay is what you're going to allow it to be g, that is the acceleration due to gravity, right? So something that we can say from this is that the velocity in the horizontal direction is going to remain constant, because there is no acceleration in the horizontal direction. This is something that we get from Newton's first law. But the velocity in the vertical direction is going to change, so we're going to have to use the equations of motion that you might have learned earlier in the vertical direction, whereas we can simply use basic equations such as x is equal to ux into t for motion in the horizontal direction. And the last thing to do before we begin would actually be getting a concrete relation between u over here, the vector u, and ux and uy. Now, as you might have already seen, we can actually resolve a vector into its rectangular components. So if we have vector u over here, I can say there's a component along the x direction and a component along the y direction, that is a rectangular component. This is supposed to be a triangle, I'm just going to complete over there. So if this is u over here, and if this is an angle theta, what I can do is I can let its component along x direction be ux, which is what we want to find over here, and let this be uy. So we can say cos theta is equal to ux, and we're going to use the magnitude of the vector here. We can't just use the vector itself. So we're just going to write u over here. So we can see that ux is equal to u cos theta, and similarly we'll find that uy is equal to u sin theta. Alright, so we're just going to keep this in mind. I'm just going to erase this to start it over here. I'll write it up there. So what we can write here is ux is equal to u cos theta, and uy is equal to u sin theta. Alright, so the first thing that we're going to try and do is derive a general equation for the trajectory of the projectile. That is, how can we describe this path in terms of y and x? I mean, sure, we can just say, oh yeah, it's a curve, sort of, but what type of curve it is, and how can you define it such that whenever we have a particular x value, we can also get a corresponding y value. So to do that, what I'm going to do is, first I'm going to try and get the expression for time. Alright, so I know that there is no acceleration in the horizontal direction, so that might be a convenient place to start. So I can write that the distance in the x direction, that is any arbitrary distance x, can be written as ux into t. Alright, and this is for any time t till the time of flight. So I can further write this as x is equal to u cos theta t. Therefore t would actually be equal to x by u cos theta. Alright, so keeping this in mind, we'll actually move on to the vertical direction, and since the vertical direction has accelerated motion, we're going to have to use our equations of motion. So we can write y is equal to uy into t minus at square by 2, but a in this case is actually equal to minus g. I mean, it's plus at square by 2, so since a is equal to minus g, or you can mention it over here. I mean, the minus direction is simply to indicate the fact that it's downward and we're assuming the positive direction is upward. So we can say y is equal to uyt minus gt square by 2. Alright, now what we're going to go do is we're going to substitute this expression of t over here in this equation. So when we do that, what we get is y is equal to, I'm going to write uy as u sin theta, so what I'll get is u sin theta into x by u cos theta. Let's put the whole over here, x by u cos theta. Alright, so u gets cut, so that's a good thing, and minus g into x square by 2u square cos square theta. Alright, so the simplified expression is simply y is equal to x tan theta minus gx square by 2u square cos square theta. So as you'll see, everything over here is a constant except for x and y. That is, theta here is the initial angle of projection, u is the initial velocity, that is the not simply the velocity along y direction or the x direction, but the actual initial velocity, the magnitude of the vector u. So we have a really convenient expression, and as a matter of fact, this can actually be compared to the general equation for a projectile, for a parabola, which is of the form ax square plus bx plus c. So where c is 0, we have x, the b over here is tan theta, and a is actually g by 2u square cos square theta. So it turns out this is actually the equation for a parabola. So any projectile projected at any angle, not including taking into account the effects of air resistance, will always follow the path of a parabola. And An interesting thing to note is that this is not generally applicable for just a projectile. You can use this analysis for any type of force that is acting that has a constant magnitude or it has a constant acceleration that it's doing. So if suppose, to give you an example, if this is instead an electric field, we would still get the same thing. Conclusion that I'm trying to get over here is that if an object is projected with an initial velocity in any direction, and there is a force acting in as a constant force, or that is a force that gives constant acceleration acting in a direction other than the direction of the velocity, the object will always follow a parabolic path. So that's something to keep in mind. So this is the general equation of a projectile. And so moving on, we're going to derive three important quantities, that is, which are useful when you're solving numericals and things like that. So the first of these quantities is the time of flight. Second is the capital H, that is the highest vertical point reached by the projectile, and this will of course be given by the point when it's vertical, when it's uy is equal to 0 basically, and r, that is the maximum, that is the horizontal distance covered by it during the time of flight. So the first thing that you're going to start with is time of the flight. I mean the total time it takes for the projectile to go up from here and then come back over there. Alright, so what we're actually going to do is we're going to work with symmetry over here, and we're going to sketch or we'll draw a dotted line to indicate the fact that this is the point at which it has reached capital H, that is, this is the highest vertical distance the projectile will achieve, and after that it will start falling down. So an interesting thing to see over here is that this path is actually symmetric. There is nothing to distinguish this side of the portion from this, this side of the path, this side of its path from this side. So what we can see is that we can also say that this projectile was launched from here, it went over like that, and then it came over here. So the result of this is that we can simply compute the time that is taken for it to reach over here, and we can say that the time of flight is actually twice the time it took to reach over here. So we can call this time the time of ascent, alright, and we can call the time that it takes for it to fall down the time of descent. Okay, which is, and since it's projectile, we say that they are equal. So we can say that t time of flight is equal to 2 time of ascent. Alright, so thing to note here is that the maximum height h is achieved when the vertical velocity is 0. And if you're not just satisfied with me stating it, you could think of it this way, right? So if the highest height is not achieved achieved at the point when the vertical velocity is not 0, then it could still climb higher in a vertical plane. Suppose it could still keep on going higher like that, and then the vertical height, this would be the point of highest height and not this, or point of maximum height and not this. So by contradiction, the vertical maximum height has to be achieved at a point where the vertical velocity is 0. So right, so following that argument, we can now say that Vy is equal to 0, alright, and we have Uy is equal to u sine theta. So applying our first equation of motion along the vertical direction, what we actually get is, I'll just state it over here, I don't really need to, but V is equal to u plus at, and we can say that 0 is equal to u sine theta, right, minus gt, or in this case is going to be time of ascent. So TA actually happens to be u sine theta by g, by just taking it to the other side, and time of flight would be equal to 2 time of ascent, so that turns out to be 2 u sine theta by g. Alright, so this is our expression for time of flight. You can vary the variables over here to get a sense of what it really means. If the projectile is launched at a higher angle, then it'll take a longer time to get back, and the time of maximum time is achieved when theta is equal to 90 degrees, that is when you launch it vertically upwards. So Secondly, we'll talk about maximum height, that is h or hm if you want to denote it like that. So we'll again use the fact that Vy is actually equal to 0, and we are going to use our third equation of motion here. So just to set it over here again, v square minus u square is equal to 2es. Now v is obviously equal to 0, so and u is here again uy, so minus u square sine square theta, because uy is obviously u sine theta, is equal to minus 2g and hm over here. Alright, so I'm going to cut the minus sign on both sides, and I'm going to take 2g to the other side to get yet another equation. This is hm is equal to u square sine square theta by 2g. Again, as you can see, maximum height is achieved when theta is equal to 90 degrees, because that's when sine theta actually gets its maximum value. Alright, so and thirdly, what we have is the expression for range, that is the maximum horizontal distance that the projectile covers during its motion. So range, if you want to see over here, is actually this distance over here. Alright, so this distance over here is r, and that's what you want to find over here. What we can actually say over here is r is equal to ux into time of light. Right, again we can use this simple equation over here because there is no acceleration in the horizontal direction. So what we can write over here is r is equal to u cos theta into 2u sin theta by g. As you will see from up here, we just derived it a few minutes ago. So this actually be u cos theta into 2u sin theta by g. And now I don't know how familiar you are with trigonometry, but we can actually write this as u square into 2, this multiplication of the u square into 2 sin theta cos theta by g. So this expression over here is actually the expression for sine 2 theta, that is twice the so suppose you have, basically we have sine 2 theta is actually equal to 2 sin theta cos theta, this expression over here. So sine of twice the angle theta over here. So this will actually simplify this to, this will actually be simplified to u square sine 2 theta by g. And this is our expression for maximum horizontal range, that is the maximum distance covered by the projectile during its motion. And of course we know that maximum is achieved when the argument of the sine function is actually 90 degrees. So we can say 2 theta is equal to 90, or pi by 2 as you would use in radians. So theta is equal to 45 degree. Okay, so this tells us that the projectile will cover the most distance horizontally when this angle over here is 45 degree, and the same thing can also be derived differentiating the function and finding the critical points and so on. So this was our, well, journey into projectile motion, simple projectile motion. The next video will be a little faster. It will talk about projection on an inclined plane, and I guess I will use a bit of calculus in that. So I will see you in the next video. Thanks for watching. Oh, and I just remembered, if you're hoping to have some sort of an homework exercise of sorts, you can try and derive the special case in which theta is actually equal to 0. That is, the projectile is actually launched somewhat like this. Alright, so ux would be equal to the vector u, or not vector u, the magnitude of the horizontal velocity would actually just be equal to u itself, the initial velocities, and uy would actually be 0 in this case. So that's sort of an exercise for you. You can try and work it out yourself and let me know what results you get. So thanks for watching. Okay.